In this video, we're going to review how MistAway's leak detection works in both the drum and tankless units. Leak detection is an important feature of the equipment because in the real world, leaks really do happen. Yard services cut lines with weed whackers, and squirrels sharpen their teeth on the tubing. It is obviously a problem for the insecticide to be sprayed uncontrolled onto the property. And without the ability to detect a leak and shut itself off, a unit can empty itself in just a few missed cycles. Before we jump into discussing how leak detection works in the equipment, let's spend a minute contrasting a leak with the controlled flow that comes out of a nozzle during a mist cycle. Let's start by observing and measuring the controlled flow from a working nozzle. We've set the pressure at the pump so that this nozzle is operating at 200 psi. If we hold this graduated cylinder under the nozzle while it is misting, like so, and remove it after 60 seconds and read it, we'll know the flow rate out of that nozzle, 45 milliliters in a minute, right where it should be based on the chart we introduced in the fundamentals videos. Now let's loosen the nozzle tip a bit and simulate a substantial leak, like this. Let's measure this for 1 minute. "900 milliliters in 30 seconds translates to 1,800 milliliters in 1 minute. Now let's try doing the same thing with a pinhole leak, like this one. "300 milliliters in 1 minute. So our single working nozzle flowed at 45 milliliters per minute. Our pinhole flowed at 300 milliliters per minute, about 7 times what our working nozzle flowed. And our large leak flowed at 1,800 milliliters per minute, about 40 times what our normal working nozzle flowed. What can you conclude from this? Well, there is a lot more flow from a nozzle circuit with a leak than the predictable flow of the same nozzle circuit without a leak. And that is the insight that MistAway's leak detection is based on. Brilliant, right? So leak detection works by comparing a predicted flow to an actual flow after each mist cycle. If the actual flow is much greater than the predicted flow, the controller detects a leak. The unit shuts down and flashes error 3 until it is manually reset. So let's talk first about predicted flow, then actual flow, and then how the controller makes the comparison. The controller calculates the predicted flow from a nozzle circuit by multiplying 3 variables together, all of which it knows because they are programmed into its memory. First, what is the flow rate of the average nozzle? As we discussed in the fundamentals videos, if the nozzle circuit is installed as it should be, the flow rate is pretty guessable, about 40 milliliters per minute. In another video, we'll tell you how you can calibrate the flow rate of your nozzle circuit and change the average flow rate value, what we call the AFR, in the data menu of the controller, so that it reflects the average nozzle flow rate on your installation. Second, how many nozzles are installed? You can count them, and you're required to program that number into the controller during the setup process. And third, how long was the mist duration? Whether it was a scheduled mist or a remote mist, that number is knowable because it is programmed into the controller, again during setup. Multiply these 3 values together to calculate the predicted flow. A sample calculation for predicted flow for a 40 nozzle circuit, misting 40 milliliters per minute per nozzle for 1 minute would be 1,600 milliliters. Now let's talk about how the controller gets the actual flow to compare to the predicted flow. The controller obtains its flow information from an electronic flow meter that looks like this. Water passing through a pinwheel in the meter causes the wheel to turn. Magnets on the outside perimeter of the spinning wheel create electronic signals that are counted and accumulated by the controller. The controller then turns that accumulated count into an estimation of the flow. Generally, for the flows we see in our systems, it is very accurate. Where is the flow meter installed? Well, it depends on whether you've got a drum or tankless unit. Take a look at this schematic of the drum unit. In the drum unit, the flow meter is installed on the discharge side of the pump, downstream of the agitation valve in the line that feeds the nozzle circuit. This is what it looks like installed on the unit. It takes a direct reading of the flow that is pumped out to the nozzle circuit. Now let's look at a schematic of the tankless unit. Here the flow meter is installed as part of the freshwater subsystem. As you learned in the Tankless 201 video, the flow meter is used in the batch makeup cycle. After a mist cycle, the controller opens the inlet solenoid valve and water flows through this meter. The controller then reads the meter and uses the value to calculate how much insecticide to dose. But it also checks the value against the predicted flow. So this is an indirect measurement, since it's not actually reading the flow through the nozzle circuit, but rather it's reading the flow of the inlet water to replace what was misted out in the previous mist cycle. So we've established how the controller arrives at the predicted flow, which it calculates, and the actual flow, which it measures. Now let's talk about the comparison it makes. Let's say the actual flow read by the controller was 1,601 milliliters, and the predicted flow calculated out to 1,600 milliliters as we did it before. Well, the actual flow is greater than the predicted flow. But would we want the controller to think it has a leak and shut the unit down? No. The difference needs to be much greater. There is the potential for error in both values. The estimated average nozzle flow rate and the predicted flow calculation could be a little wrong. Or like any physical measuring device, there could be errors in the flow meter reading and the actual flow. Besides, as we learned at the beginning of the video, leaks aren't usually subtle things. When you've got a leak, there's likely to be a big difference between the actual and predicted flow. So to make sure the unit doesn't make that error in judgment, we apply what we call a tolerance factor to the comparison. This factor is expressed as a percentage of the predicted flow, and its default value is 75%. For the unit to register a leak, the actual flow has to be greater than 175% of the predicted flow. To illustrate, let's go back to our example where the predicted flow was 1,600 milliliters. We calculate the tolerance as 1,200, which is 75% of 1,600. Then we add that to the predicted flow to get 2,800 milliliters. Now let's say the unit runs and the flow meter returns an actual flow of 2,000 milliliters. The controller then compares the actual flow to our 2,800 milliliter threshold. Since 2,000 is less than 2,800, the unit determines there is no leak, even though the actual flow is larger than our 1,600 milliliters of predicted flow. It was still within our tolerance. Now let's say the unit runs and the flow meter returns an actual flow of 3,200 milliliters. In this case, the actual flow of 3,200 milliliters is greater than our 2,800 threshold. So the unit would recognize a leak, shut itself down, and enunciate a problem. If you've got an especially small or large nozzle circuit, it is a good idea to customize the tolerance level in the data menu of the controller. Generally, this means setting it at 75% for nozzle circuits that have less than 30 nozzles, 50% for nozzle circuits between 30 and 50 nozzles, and reducing it to 25% for nozzle circuits that have more than 50 nozzles. We'll touch on that topic again in the video covering initial unit setup. So now you know how leak detection works in MistAway's drum and tankless units. We think it is an important feature and one that really distinguishes our equipment.